Hello and welcome to Advent of Code. Getting ready for day 7 here. It's about 50 seconds to go before the next problem becomes live. The leaderboard remains elusive for us so far this year. Only 2 days have I gotten points for my stars, but if you look at some of the scores that we have so far, getting into the top 100 is only one, or 2 good days away. So, any night could be anyone's night. Let's just see which night gives us. About 15 seconds here. Uh, let's get something. Let's get something that's maybe suited to closure. That would be that'd be a nice surprise. All right, here we go. All right, Recursive Circus. The program. Interesting. Huh. Structure of these towers. Programmed to yell out their name, weight, and if they're holding a disk. Interesting. Recreate the structure. Ah, okay, so they're kind of like defining a tree here. All right. What is the name of the bottom program? The bottom of the tree that points to everyone. So in this case, how could we do something like this? Well, let's save this input. The name of the bottom program is going to be something that nobody points to. So what would just happen if I would just look for all the lines that contained maybe this, and then I only looked at, maybe I did like well, let's make sure we understand the program here. Okay, so that does seem like something that might work. So maybe what we can do is we can read this in as input here. Okay, and this is going to come in as sequences of things. So if I take this and I do something like map, I want to drop 2 from each of these. Drop 2 from each of these lines here, and then I would also want to. Okay, so this is going to give us all the things that are pointed to, and then I think I also want to. Actually, I think I can do map cat, and then maybe something like map. For each of these strings, I want to replace the comma with nothing. How does this work? Yep, so each of these strings like this. And then I could maybe make like a set of these, and then maybe compare that to what I get from mapping the first to these things. So just map the first, and so let's call this a set of things, and then I think require closure set like this, and say something like I want to take the set difference of this and this here, which should contain, see, one element, different kind of threading. Let's try this. Correct, rank 25, pretty good. All right, now I guess we're probably going to have to build the tree. They can't get down. They could get down if they weren't expending all the energy trying to keep the tower balanced. One program has the wrong weight. I see. Each program standing on that disk forms a subtower. Each of the subtowers are supposed to be the same weight, so that the disk itself isn't balanced. The weight of a tower is the sum of the weights of the program in that tower. Okay. Given that exactly, what would its weight need to be? Okay, so if we look, okay, all right. So we got to find, yeah, we got to like find the bug. Um, so my guess is that if we look for that program here, so this says 57. So I guess I don't understand quite how weights work here. So in the example, for this disk to be balanced, must all have the same weight. For this, standing on and all programs above it. So let's see. So this is saying that all right, don't quite understand it yet. So I think what it's saying is that okay, let's look at GYXO, EBII, JTPL. Okay, yes, yes, yes. Here we go. GYXO, JTPL. Okay, they all do have the same weight. And oh, I see. I see. Okay, because these are all okay, so because these are all siblings, they all have to have the same. Okay, all right. So we sort of have to do. So maybe we could say a tree is balanced if it's the case that every and now we're gonna have to represent a tree. Let's see what is going to be a good way of representing it. Maybe maybe we'll have some kind of we'll have like a links structure and then a node that we're on, or actually probably more like this. So what we're going to do is for every one of these nodes, for every one of the okay, so the node itself is going to have like children, I guess. And if for every one of these children, it's the case that we'll use the links. Maybe this should be like the tree, and we'll like maybe we should do something like the links and the values. I think I kind of like that. So or maybe like children values. Okay. So we like a note. Right. So if we look up the children of the node, and then we're going to apply equals to map values to the node, something like that. All right, and at this time, we probably need to write a parsing function also. So the output of parse is going to have three things. So I think we can do a regex match here. Let's see if we already have this somewhere in the. Okay, we got. Yeah, this is not going to be too bad. All right, so given one of these lines, we know that it's going to match. Maybe we can let's just take these, instead of using a regex, let's just take these as the words, which we've already parsed. And we're going to say that okay, so let the node be first of the words, and then value be read. Let's see, what's a good way to, we could just use maybe like this here, read string of a regex match on, or I guess the second of a regex match on dot capture, and then a dot on the second of words. Okay, and then let me just say n weight and children. Okay, so the second of, yep, this is right, and then change this to weight. Okay, so here's the value, and then the children So what do we need to do to them? We basically need to, okay, there's an empty thing in here that we don't care about. Okay, and then with the children, like our CC, we just need to map our string replace here. Okay, children. All right, and then we can just make the node, the weight, and the children like this, or CC rather, and value. All right. Given that, can we do parse the first of input? Don't know how to. Did we not define input? Looks like no. Okay. So input is this. Okay. All right. That looks correct. Let's just map parse to input. Okay. Yeah. This looks fine. Okay. So then now, what do we got to do? So now let's make a tree structure here. So I think we can just say, especially if we change the way this parse works here, we could actually just use into a map. Okay, so all right, so this is looking pretty good. So here's our tree. All right, now what? And then we know that our root is the value that we passed in here. Okay, so now given this structure, we're basically asking balanced tree on a node. So now what? We still want to get the children, but now getting the children out means taking the second of look the node up in the tree. And the values is a function where we just get the first of looking something up in the tree. Okay, so this is, are all of the children balanced? So let's take the first of the keys of the tree here. Okay, and ask if it's the case that it's balanced. All right, and it says I need a node. Right, I need the actual tree. So here we go. Okay, and it's saying it doesn't have any children. Okay, that makes sense. So let's just say, and there have to be children. Or I would say, so we're saying that root nodes are balanced. Okay, so then this makes sense. And then how about the second one of these? Let's take a look here. Okay, so let's, how many is this? Oops. Okay, it's either 9 or 10, so. Okay, so this seems to be saying that this particular tree is not balanced, that all of its children don't have the right numbers. So if I look down, I see 359 and 359 and 65. So what would its weight need to be to balance the entire tower? Okay, how about I actually want to map balanced to the keys because I want to see what the balance situation is. Okay, so the situation here, I think that what we could do is maybe go through each of these possibilities and replace the node that it's complaining about. And then, like, I guess, try setting it to a correct value and see if that makes the tree all balanced. Maybe like all balanced tree T is where it's the case that all right. So let me see how many children these have here. Okay, so it would kind of be nice if this balanced function returned let's see, if it returned a list of possibilities to check. So, so we could do something like, okay, so let's maybe have a different function. Possible solutions here. For a tree in a node, we're going to perform this lookup on the children. Okay, so these are all of the child. These are all the child values, and then I think we want to do something like maybe we can like take the frequencies of this and do something like for each of these pairs. So let's see. So okay, so we need to say for the child C in the children here. Maybe I'm going to do this. Okay, so maybe like let F be these frequencies here and say something like for each of the children, if it's the case that I look up the child in the frequencies and it's 1, in other words, it's the odd one out, then then why don't we just return something like try that child along with a value here v, which I'll define as saying, I'll say the children values are this, f is the frequencies of these values here, and then we'll say the things that we're going to try in values, all of these. So this might result in a little extra work, but let's just try this first one here. So if I said, what are the possible solutions for our tree for this node? And it says you could try changing this to this, 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 this to this. Okay, this seems tractable. So I think what we want to do is maybe like for C in the keys of the tree, for a possible solution S, we're gonna let the solved tree be, I guess, something like apply update to the tree with S. Is that, no, that's not quite right. I'm going to destructure this and say node and value. The solved tree is going to be update in the tree node value. Nope. Yeah. Okay. Update in the update tree. We got node here. All right, so we should just be able to say associate in this structure at point 0 the value v. And then we want to say when the solved tree is all balanced, let's emit something like the solved tree, the node, and the value. Okay. All right, nothing has come back yet. It's possible that I wasn't right about the tractability. We can get a quick estimate on that by doing something like a map cat of possible solutions. Let's see. So we should actually probably have a fast fail similar to this here. If there are no children, and just return an empty list like this. Okay. So connect another little REPL here and say, all right, this is my redefinition of possible solutions, map cat, possible solutions on tree for each of the nodes in the tree and apply plus to it. Vector can't be cast to can't be cast to a number. Is it saying that this is returning lists of vectors? Oh, yeah, that makes sense. Okay, so maybe something like map the second. No, we just want to count. That's why. Okay, so let's count these up. It's 4791, which makes me think, wow, why is this taking so long? That's really surprising. If there's only 4,700 different things to try, I mean, how long does all balanced even take to run? Time running all balanced on the tree here. Switch to this REPL. Is my all balanced not? Oh, my all balanced is not correct at all. I think it's getting stuck trying to like print this out or something. Yeah, okay. So it's got to be the case that, so I think we got to say every. I think that's the right way. Okay. Yeah, I think it's getting stuck in trying to print out a big value. All right. So now we have all balanced here. Okay. Okay. Good. Time all balanced on my starting tree. Okay, false. All right, so let's try this now. It says we tried everything and nothing worked. Okay. What if we just get the first here and take this restriction out? Okay, so this is saying we took this value and replaced it with this. I want to be sure that they actually did that. So let's get a little Vim going. Take a look for this value here. Okay. Oh. All right, so it says that worked. Okay, so it says that it made the change. All right, I guess I'm misunderstanding the problem. Okay, so it says that this stack is heavier than it should be. It needs to be 8 units lighter, which means it has to be, all right. So given some input here, so if this was the tree, something like input 2, tree 2, and I guess we need a root 2 as well, to help me not get confused. So here, and then this should be fine. And then the root 2 is all right, like this. Okay, and so if I run possible solutions on tree 2 for the node, so we're supposed to suggest a fix for this one. Okay, and it says no. It says that's not okay. All right, so is it because we're getting stuck here? Probably. If it's not the case that there's anything here, so what? So this, so tree 2 should have something there. Am I not parsing it right? No. Okay. Nope, here it is. Which means what? What are the keys of tree 2? Oh, all right. Looks like for whatever reason it's not this. It's just the old tree. Okay. Well, that would explain if no. Oh, I see. It's this right here. Okay. So possible solutions. Okay. Mm-hmm. Okay. I think I kind of see what's going on here. All right. So this one doesn't have to change. So the possible solutions are actually going to be on this guy here, which doesn't include changing UGML. I see. Okay, the way that I'm generating the possible solutions is wrong. Okay, because yeah, I'm trying to put it in line with these other ones, but really what I need to do is compare it to what the sum actually should be. Okay. All right. So, well, let's try this. Let's at least see if it's the case that when I call all balanced on tree 2 after doing this update thing. So update tree, the node is going to be this guy, and then associate the value here with 60. All right, so all balanced still returns false, which means that my all balanced is not correct. Okay, so I think we need like a recursive, like maybe a recursively defined wait function. Where we say something like let C be the children here, and we are going to look, I guess, at each of their weights. So add all their weights together. Okay, so maybe just apply plus to, and then we also need to get the weight that we have here. So so then we could say something like weight tree to UGML. A string can't be cast to number. Yep. Okay, so here we go. All right, so there's our 251. So then I think our balanced needs to become, is it the case that, so it isn't comp first tree here. I think it's weight tree node. All right, so now is this all balanced? So this is all balanced, yes. Without this, if we don't update the tree, then it isn't balanced. Okay, so we have that at least. Now we need to make it so that the possible solutions includes the right thing. So basically, I wonder if we could like maybe short circuit this, where we just say like there are possible solutions. We just go like range -20 to +20 and hope the value's in that range. Maybe that won't take forever to do, and then we would have to do like an update here. Okay, and then oh right, and then this would have to be like a C. Yeah, let's try this. Let's try this sort of hacky thing. Oh right, update at point 0. The function is going to be plus. Yeah, so I think so. If we were talking about like 2,700 things before, then now we're talking about like 100,000 things now. So this might not be tractable. And then the other thing that could happen is that it that our solution just isn't in the range -20 to +20, or -20 to +19. So so let's leave this running, but not rely on it. Okay, so in this case, what are we going to do? So we're going to say, so for these, so I think we don't care so much about these values here. So we basically, so we want to get all the weights out. So let's see. So we're getting the weights of all the children, and then yeah, we could just say like for each of these. No. Okay, well, you know what we could do is we could take like the combinations of ways that we could take the two children. We could say to each of the children, like, you try being like this other one. Let's get over here. So we could say something like child 1, child 2 in the combinations. Where are we at? Okay. Okay, the ways of taking 2 of these children here. And then we're going to say, let the weight 1, weight tree, okay, weight 2, same deal. All right, and then I guess we can further stipulate when these 2 are not equal. So when it's a possibility that they matter. Okay, so we're going to say let the difference be subtract from weight 2 from weight 1. And then the change that we're going to try is we take C1 and we set its value to, so if this is the difference, so let's just say like C1 is at 10 and the other one's at 20. So in that case, we got negative 10 here. So in the case of C1, we've got to subtract from its value, which is going to be this tree C1, the difference. And then the other thing that we want to try is C2, where we add this value here, the diff. Okay. So, and then I just need to do a little unrolling of this for comprehension. Okay, emit X. Okay, this stuff all goes away. Try doing this. All right, possible solutions. Okay, well, that's in there. All right, so let's try this. All right, nothing coming back yet. Out of memory error. Okay. I hope I don't have to restart the REPL, but if I do, then that will hopefully be okay. Oh, geez, it's not too happy about this. Let's see how this REPL's doing. Okay, we got a little bit here. Oh, did something come back? Oh, come on, Eclipse. All right, so this says that the corrected value is this 827. What would its weight need to be? All right, let's try 827. Not the right answer. If you're stuck, okay. All right, so Eclipse, I think, is having trouble because I guess the tree was bigger than I thought. So maybe there was like more than one solution here. So let's try this instead. Oh, and also, yeah, I got rid of this thing. Yeah, no wonder it had trouble. Okay. All right, so let's try the first of solutions. Nil. Okay. All right, fair. Oh, right. And then this needs to go back to being an assoc. Right. First of solutions. Still nil. Okay. So let's try changing this, I guess, to T2. Tree 2, rather. All right. This should be fine. Okay, so here it works. Here it knows that here it recognizes that it can make that one change and then things work. But on the bigger tree, it doesn't. All right, let's go back to the problem statement here. Let's see, what would its weight need to be? It needs to be 8 units lighter for its stack to weigh this much and keep the towers balanced. Hmm. Should we look for maybe we should look for the first. Hmm. Hmm. Add. You print out all the parts here that aren't balanced. Something like each of these values uh, and right here when not balanced tn this, and then yeah, let's try here. So it's saying this node, which was the root node, is not balanced. Okay, and then if we do this on this tree, and this is saying that this is the collection of nodes. This is the collection of nodes that are having a problem here. Which I get that multiple nodes would be having a problem. It's just not clear to me why the solution as presented doesn't work. So maybe we should count these things here. 510. That doesn't seem like a lot if there are this many. If there are this many possibilities, maybe what we could do is we could look at just the nodes. This is a little big, but not super big. So basically, we should expect that any node that's represented here, well, so this isn't quite right because it's going to be like the children of these nodes are the ones that potentially have a problem. But I think there should be a lot of overlap because this is going to be just like a subtree here. So if we look for, yeah, so we see you can try changing this value to this. So maybe we could modify the input to make a tree that's a little bit more challenging. What would its given that exactly one program is the wrong weight, what would its weight need to be to balance the entire tower? And we submitted our 827, which I guess well, this actually did give us a solution, right? Maybe we should look at the solution in more depth here. So let's Yeah, closure REPL has always got a pretty substantial buffer, so you need to make sure that before you run the program for real that you take out some of these debug print lines. Okay, so here's a solution. All right, and this is going to contain the tree, but okay. Oh, actually, no, it isn't. So, oh wait, what did I change something again? Da, 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 da. I'm afraid that I did change something. Here, let's try this. Oop. All right, let's see. All balanced here. Okay, that's true. That's false. Uh, possible solutions. Tree 2 on T. Oh, here it's up there. All right, is this working? This is suggesting the right answer. So, okay, possible solutions is suggesting the right answer. Solved tree seems to be doing the right thing. Oh, I see. So that'll help. Okay. So in this case, oh, I see. We were already at. Okay. Okay. So it says change UGML to 60, which is checking here. Its weight would be 60. What would its weight need to be to balance the entire tower? Okay. So here it works, but changing it here is not working. Okay. Okay. Let's All right, let's get the first thing tried. No care for the answer. So this is saying you should try setting this to this. Okay, did that work? This value. So yes, that seems like did work. Okay, my guess is that my possible solutions is not. It's not suggesting the right thing. So let's see. So this seems like we're taking each combination of the children of a certain node, and then when their weights don't add up, what we try doing is we try setting the weight of each of these to be what it would take to make it equal to the other one. So I don't think that I screwed up the plus minus stuff here, but I guess it's possible. And it seems like quick enough to check. So if I set this and say, turn this back on, still doesn't work. Okay, so in this case, what I'm going to expect is at least the count of these things that I'm trying should at least be doubled, which that does look like it is. Right? Okay, so if two subtrees are not balanced, huh? Huh. So maybe, well, I guess maybe we can just put something in here, like say C1, C2, weight 1, weight 2, like this, and just try. Let's try just to take 10 of these here. That should be fine as long as I use do run. Okay, and it's saying that these weights aren't equal. Um, maybe the answer is in the way that maybe there's something about possible solutions that makes it accidentally true for tree 2 here. So this is saying that, so okay, in this case, it says that there are only 2 things to try. This disk is unbalanced, which we recognize. This stack is heavier than the other 2. Even though the other ones are unbalanced, this one is too heavy, it needs to be lighter. If this change were made, its weight would be 60, which we got. Given that exactly one program is the wrong weight, what would its weight need to be to balance the whole tower? Well, let's I guess let's try to identify the part of the tower that has a bug. So, all right, let's change this back here to the thing that's just looking for one solution on tree. Okay. Okay, go back to our print line here. This print line, I'll take this up. Okay, so why don't we start with, like, for each of the keys here, we're going to emit, like, let's do like maybe a group by balanced, like this here on tree. Keys of the tree, and then balanced, I'm just going to double check, returns a Boolean. It looks like it does. All right. So let's take a look here. So this is hard to read. How about a count? So it should be true and false, right? All right. How about the count of true? Okay. The count of false, 28. So it's saying that there are 28 nodes that have a problem. Okay, so then what if we do this? So for each of the nodes that has a problem, can we just print out, like, the node and also its value and its children? This should be pretty short here. Okay. And let's see. So from this, so these are all They're all unbalanced. What happens if I make something like input 3? Where maybe it'll be better if I change the print line, change this to like a print line where we do node followed by like this, and then like one of these, and okay, and then the lack of commas shouldn't matter. So if we do this, then what would happen if we asked what the root of this one was? It would say this guy here, which is, was this the answer from the root in the beginning? Yes. Okay. So I think this all makes sense because somewhere here there's a okay, I think I might be able to do, I think I can follow each of these children and see where the problem is, because so it's saying that this node is not balanced and this node is not balanced. Let me look at my definition of balanced. Maybe the definition of weight is wrong. Some of the weights in the, yeah, my definition of weight is wrong. So this shouldn't be comp weight, comp first tree. This should be like partial tree, no, partial weight tree like this. Okay, and then do things still work here? Yes. And then do things still work here? This is a solution. I suppose it wouldn't hurt too much at this point to just see what my count of solutions is. 6? Well, actually, that might actually, if I just do something like map drop 1 to here. Yeah, okay. All right, so providing this answer, submit, rank 5, 45. All right. So let's look at the advent calendar here. All right. Okay, filling in. Was happy to get on the daily leaderboard for the first star at least. So first star. Yeah, 25th place in 3 minutes. Took a long time to do part 2. Let's see how long other folks took to do part 2. Okay, about 25 minutes. So yeah, it's okay. So it took me almost an hour to do part 2. Yeah, let's talk about the problem. So this is our first tree problem of Advent of Code. So that was so that's just a lot of fun. And in this case, it's a weighted tree um, defined by the input that we have here. So pretty straightforward kind of thing. And part one is just basically a warm up. Given a collection of links, can you find or given a tree, can you return the root? What they call the bottom program, and that's almost just a text processing problem. You could probably do it in Bash. Yeah, you're essentially the root is the one that doesn't have anything pointing to it. So I was thinking about doing it with just Bash. That would be something like yeah, it's tricky because you don't want to include, oh no, I think this works. So you would want to say something like, how would you do this? So you want to look for everything that has that arrow. All right. So get everything that has the arrow, and then I think you could use something like, maybe like you could use like tr for commas, turn commas into new lines, and then let's see what else. I think you could do like a sed on maybe this arrow thing itself, and then I don't know what a sed new line looks like. Yeah, that's not it. Something like that. Yeah. Some combination of these things. If you like bring in Vim, for example, you could like maybe try to use a macro where you would like look for this thing and like change it to that, then find the next one, and then so basically now in this situation, you have all of your candidates, which are the ones that have the parens with them. Maybe substitute all instances of space, something like this. So all your candidates are the ones with parens. So if I have my like ABC file here, and then maybe like grep for, that should work. So I can maybe get just the, so these would be like the candidates. And then if I grep for without this thing in temp ABC, then these would be like the excludes. And then I think you can do like a grep based on a file. Temp excludes in the candidates like this. Yeah. So there's a bashy type way to do it, and probably a way to do it with like a big just like a single big command line invocation, maybe. But so this can actually be gotten pretty quickly and doesn't require really any parsing, any serious parsing, or tree manipulation or anything. But okay, then we get to part two, and now it's time to like actually use like a recursive algorithm. And where I got stuck, and the reason that I spent 30 minutes debugging my program is that my my program worked for a tree that had that was exactly this deep, but it didn't work for trees that were any bigger than that. So yeah, my big mistake. So yeah, my big mistake was just basically defining the wrong, defining weight in the wrong way, and sort of playing fast and loose with the difference between like a weight and a value. And yeah, so the representation that I chose for the tree was a mapping from nodes to tuples, basically. And then each tuple had the value at that node and then its children. And this was okay. This was pretty convenient to work with. Yeah, my definition of balanced initially used just values instead of weight. It actually took a while for me to actually write this weight function, and then when I wrote it wrong, because I instead of mapping just the recursively the weights of the children, I took just the values. So this weight here works on leaf nodes. It just returns the value of the leaf node extracted here, and then on anything that isn't a leaf node, it's it basically sums everything up. So yeah, that was the big bug. And then yeah, balanced check here, pretty straightforward definition. And then yeah, what I ended up going with, I tried a few different general approaches, but yeah, this part was funny here. I wonder if this would have worked. I wonder how far this particular value had to change in the tree. So 1869, 1864. Oh, so it this actually would have hit the value, although it wouldn't have told me so, because my definition of weight was still broken. Yeah. So what the solution that I ended up happening on was, so initially what I was trying to do was I was trying to use like some kind of like majority algorithm and say that if you are alone in what your value is, then see if you try to become like everybody else. And maybe if we needed things to be really efficient, then we could do it that way. But this worked just as well, and I think it's a lot easier to reason about, which is to take all the pairs of children at the point that you're looking at, look at their weights. If their weights aren't the same, take the difference, and then apply that difference. And then, yeah, my guess is that this will still work. Probably produce only half the solutions here. I wonder why there. I wonder why there are still 4 of these. Oh, it must be because. Oh, and this wouldn't have anything to do with it. Yeah, it must be because it's at a point in the tree where there are 5. Yeah, I guess there must be 5 of these at this point in the tree. Anyway, so yeah, I just basically iterate on all the possible solutions, and then for each of the possible solutions, which is represented as take this node and try this value, produce a new solved tree by editing the tree, and then check whether everything's all balanced. So yeah, there's probably an approach where it does more like tree traversal and just analysis in order to like find the exact node. I just tried pretty much every reasonable possibility and got a solution pretty quickly. So, all right, longer day than usual, but a lot of fun, and happy to have gotten some points. I think I got 70, 75 or so points today. So if we can keep that up, we'll be on the leaderboard in no time. What are we shooting for here? Looks like, yeah, 217 is the cutoff. So exciting stuff. Looking forward to the rest of the month leading up to Christmas. And if you've made it all this way through the video, then hope you join in tomorrow. And thanks for watching.